In this lecture, we'll consider when we can consider two species to be exactly the same. This notion is captured by the isomorphism of species. So let me just give you the definition first. So suppose we have two species of structures. F and G are said to be isomorphic if for every finite set U, there exists a bijection phi. It depends, the bijection depends on U, so I'll call it phi sub U from Fu onto Gu. And this bijection needs to respect transport of structure. What does that mean? For every bijection between finite sets sigma U to V, we have on the one hand we have from Fu to Fv we have F sigma. On the other hand, from Gu to Gv we have G sigma. And now from Fu to Gu we have phi U, and from Fv to Gv we have phi V. These are all bijections. This diagram commutes. What does it mean to say that this diagram commutes? This is just means to say that if you take G sigma circle composed with phi U, this is the same as phi V composed with F sigma. Both these are functions from Fu to G of V. Those of you who are familiar with category theory will recognize this as so species are nothing but functors from the category of finite sets with bijections for morphisms. And in category theory language, this is an isomorphism of functors. Actually, it's a natural isomorphism of functors, so I'll just call it natural isomorphism. So if two species are isomorphic, we treat them as the same. We treat them as being exactly the same, and they will in fact have many of the properties in common. And we write F is equal to G if F is isomorphic to G as a species. Okay, so let me give you an example which illustrates this. Basically what it means is that they may look slightly different in the way they are defined, but for all practical purposes they are the same. So let's define a species inv circle 0 of U. So this is going to be all those permutations of U such that sigma squared is the identity of U. So all permutations whose square is the identity, they are called involutions sometimes, but which have no fixed points. Sigma U is not equal to U for any U in U. So these are called fixed point free involutions. Now, for example, if you have 1, 2, 3, 4, then a fixed point free involution here is, say, something which takes 1 to 2, 2 to 1, 3 to 4, and 4 to 3. That's an example of a fixed point free involution. So it leaves no points fixed, and it consists, it's an involution. So that means it's entirely consists of only 2 cycles. It only has it's a permutation which only has 2 cycles. And the other species that I'll be considering is M2 of U, which I'll call the species. So this is going to be perfect matchings on the complete graph on U. So the complete graph on U, well, it looks like this. So let's say the set with 4 points, then the complete graph looks like this. All possible edges. And an example of a perfect matching on this graph could be where you match 1 to 2 and 3 to 4. And these are essentially the same. These species are isomorphic. Let me give you the definition of phi u given S belongs to inv 0 of U. Define phi u of S to be the matching that matches U belongs to U to SU belongs to U for all U in U. So under this function phi u, these two, this fixed point free involution that I've drawn up here and this perfect matching of the complete graph on 4 elements, they correspond to each other because this involution takes 1 to 2 and 2 to 1. I've matched 1 and 2. It takes 3 to 4 and 4 to 3. I've matched 3 and 4. So these are isomorphic species, and you can check that this phi u will satisfy this compatibility condition with transport of structures. Now, as I was saying, isomorphic species have all the same properties as far as species theoretic concerns are involved. And one formalization of this is the following theorem. If F is isomorphic to G, I'm writing equal to here, then the cycle index generating series for F is equal to the cycle index generating series for G. And the proof is, well, not very difficult. You just go through the definitions. So recall that ZF is just sum n greater than or equal to 0, 1 over n factorial, summation sigma in Sn. And then we have to take the fixed points of Fn under F sigma. Count those, and then we have product of xi to the power sigma I. And similarly, Zg is given by a similar sum Gx, not x here, it should be n. And these will be equal if we can show that these sets have the same cardinality. The bijection phi n. So this is going to be from Fn to Gn. will map Fn F sigma onto Gn. Oops, this should be G sigma, not F sigma. G fixed points. Gn G sigma. That's just because of this naturality property that G sigma circle phi u is phi v circle F sigma. Because what we have is that if you take G sigma circle phi u of S, well, this is equal to by that property it's phi, so this phi is going from n to n, so let's write it like that. So it's again phi n, v is also n, circle F sigma of S. And if S is a fixed point of F sigma, so F sigma S is equal to S, under this condition this is equal to just phi n of F sigma S is equal to S, this is just phi n of S. And so what we have is G sigma of phi n of S is equal to phi n of S. So this means that phi n of S is a fixed point of G sigma. So G sigma phi n of S is equal to phi n of S. An immediate corollary of this theorem is that both the generating series and the type generating series of isomorphic species are the same. If f is isomorphic to G, then f of x is equal to G of x and f tilde x is equal to G tilde x. And this of course is obvious because we know how to compute f and g in terms of the cycle index generating series. So f of x is zf x comma 0 comma 0 and f tilde x is zf x comma x squared comma x cubed. So if the cycle index generating series are the same, then so of course also the generating series and the type generating series will be the same. Now it's possible that the generating series, the exponential generating series of two species are the same, but the species are not isomorphic. So last lecture we computed the generating series of the species E and the species L. So recall that ZE of x1, x2, this is product of I greater than or equal to 1, 1 over 1 minus xi, and ZL of x1, x2, this is just 1 over 1 minus x1. And yet what we have is Ex is 1 over 1 minus x and Lx is also 1 over 1 minus x. So what we have is that EU has the same cardinality as LU, but E is not isomorphic to L. So there's a weaker definition than isomorphism, which is called equipotence. Species F and G are said to be equipotent if for every finite set U we have that the cardinality of Fu is equal to the cardinality of Gu. So L and E are equipotent but not isomorphic. In fact, equipotence is exactly equivalent to saying that the exponential generating series of the species are the same.